voltage. So here if you come back here in the RC series circuit, so we have taken the reference as current, and this is voltage, and in this so see the voltage waveform. This is the resultant voltage what you are getting. So current leads the voltage, so by an angle phi here. So there is a difference, a slight difference in RC series circuit when compared to RL series circuit. So instantaneous power P, come back to instantaneous power P once again, that is equal to V into I. That is Vm sin omega t, the instantaneous voltage that you are applying, and the current here is Im sin omega t plus phi. So if you deduce this equation, if you solve this equation, Vm Im sin omega t into sin of omega t plus phi. So once again you have to solve this equation by using 2 sin A sin B formula, and at the end that what you are getting is P is equal to half Vm Im cos phi. And before that one step, once again we are getting two terms for this power equation. One is periodically varying term whose frequency is double the frequency of apply voltage and can be neglected, because if we integrate this over a period of time, its value will be 0. So that we can consider only the positive term, half Vm Im cos phi, and once again this can also be written as Vm by root 2 into Im by root 2 into cos phi. So that is Vm by root 2 is equal to Vrms, Im by root 2 is equal to Irms, and cos phi as it is. So once again the power equation will remain same, P is equal to Vrms into Irms into cos phi. So Z here is equal to R square plus Xc square, because here capacitance exists. So RC or XC R square plus Xc square, Z the impedance of the circuit. Impedance is a combination of resistance and inductive reactance here. Here there is no inductance. Here capacitive reactance, is a capacitive reactance, R square plus Xc square. So that you would remember here. So this is the power triangle. So this is the voltage triangle as before, I into R, and here this is the voltage drop across capacitance. In the previous circuit you can see, so this triangle it moved upside because the current lags. Here current leads the voltage. So if the current leads the voltage, means this voltage vector diagram, it has to come down here, so that the resultant waveform, the resultant voltage E is equal to I into Z. So see the angle, this is the phi is the power factor angle. Current leads the voltage, the resultant voltage E, by an angle phi. This is the voltage drop across resistance, this is the voltage drop across capacitance. So this is the total voltage of the circuit, and this is the current, total current. Since it is a series circuit, only one current present, so this has taken as reference. So this is the total current and this is the total voltage. Total current leads the total voltage by an angle phi. Whichever comes in first when you are moving from clockwise direction, that you have to take as a leading, and whichever comes next, that we can take it as lagging. So in this circuit, current leads the voltage by an angle phi, the power factor angle phi. Okay, so phi is equal to tan inverse Xc by R. The power factor can be calculated in this formula. Phi is equal to tan inverse Xc by R. So this is the power waveform. Once again, if we consider the V is equal to Vm sin omega t, that we can consider here is a very solid one. And next is the current waveform which leads. So how we can see the how to draw the leading waveform? So that I already told in the class. So this is V is equal to Vm sin omega t is started from here 0, but here I is equal to Im sin omega t plus phi is already starting. So you have to draw from here. It is not 0, it has got some value. I is equal to Im sin omega t has plus phi has got some value when V is equal to 0. Current has got some value when V is equal to 0. That means to say current leads the voltage. So that you can draw like this. So it goes like this. It has to go like this. So that you have to make practice at your home to draw this. So once again, if you consider the power triangle here, so 0 to pi by 2, if you consider P0 to pi by 2, so voltage it is positive and current is positive, and the power triangle is it reaches its peak, it's a positive. So when pi by 2 to pi, if you consider pi by 2 to pi, see here the current is negative here. So current was the current waveform. So current waveform, it goes here negative, and voltage was the voltage waveform. So even if the voltage is positive, it move towards 0. So is positive, the power is negative. It moves like this, and it moves like this. Once again, in the next pi 2, 3 pi by 2, and so both are negative, so power is positive, because power is equal to voltage into current. If voltage and current both are negative, power will be positive. So that you have to observe. So like that you have to draw the power waveform, voltage, current and power waveform. The last one is a series RLC circuit. That is very peculiar and very important. In this circuit that we are considering three components. One is resistance, inductance and capacitance. By knowing the value of without knowing the value of inductance and capacitance, we cannot say or we cannot predict which one the current is lagging or leading in the circuit, because the current depends upon inductance as well as capacitance. Because resistance, through resistance, even if current flows in the pure resistive circuit, current is in phase with voltage, no difference. But when inductance and capacitance comes, current will be lagging or leading. Here both are present, inductance and capacitance along with resistance are present. So it depends upon the value of inductance or inductive reactance or capacitive reactance, which decides whether the current is lagging or leading. So once again, when alternating voltage V is equal to Vm sin omega t is applied to the circuit, current starts flowing in the circuit. So VR is the voltage drop across the resistance, I into R, I into XL. So that is the voltage drop across inductance. So I into XC, voltage drop across capacitance. So here leading current, so voltage leads the current or current lags behind voltage. So that's important. You should not get confused. You have to stick to only one, whether current is lagging or voltage is leading. So better take only current. Current lags behind the voltage by an angle 90 degree. In the pure inductive circuit, current leads the voltage by an angle 90 degree with the pure capacitive circuit. But if you consider all three combination here, the XL or XC that decides whether current is lagging or leading. Yes, impedance is given by Z is equal to R square plus XL minus XC whole square or XC minus XL whole square. Because case first, if you consider the first case, here XL is greater than XC. So XL is greater than XC. See the triangle here, so voltage triangle. This is ER is equal to I into R. There is a voltage drop across resistance as usual. So this is the current I as taken as reference. Voltage is in phase with the current, no problem at all for resistance. Since XL is greater than XC, so this is XC, because XC is minimal when compared to XL. So XL, I into XL, since XL is greater, the voltage drop across inductance is greater, so the magnitude of the voltage drop is shown great here when compared to EC. So EL is greater than EC, so the magnitude of EL is shown greater when compared to EC. Since XL is greater than XC, so this is the triangle. So yes, the resultant goes towards the inductive reactance or EL. The resultant, because XL is greater than XC, so inductive effect is more than the capacitive effect. Since inductive effect is more than the capacitive effect, that you can observe here, the resultant EL minus EC. So this point indicates EL minus EC is equal to I into XL minus XC. So the whole circuit will become inductive. because inductive reactance effect. That means to say, when whole circuit become inductive, current lags behind the voltage by an angle phi. Once again, I cannot consider this exactly 90 degree because it is not pure inductive circuit. So from the vector diagram, we can observe that current lags behind the voltage by an angle phi, that I already seen. I will explain. The impedance triangle is given by I is equal to E by Z. So once again, in the RL series circuit, if it converts into RL series circuit, then the phi lags behind, that means the current lags behind the voltage, then everything turns towards the RL series circuit. V is equal to Vm sin omega t, I is equal to Im sin omega t minus phi, because the current lags behind the voltage by an angle phi. So this is already we have seen. If V is equal to Vm sin omega t and I is equal to Im sin omega t, what may be the equation for power? That you have already seen in RL series circuit, because the effective will become inductance because of the XL is greater than XC. So P is equal to EI cos phi as before. So where E and I are RMS values, but in exam you need to derive all this once again, just like what you derived in series RL series circuits. So when XL is less than XC, what may happen? When XL is less than XC, that means say capacitive reactance is more. When capacitive reactance is more, Z is equal to R square root of R square plus XC minus XL whole square. It has to, because XC is greater now. And see the change in diagram, the vector diagram. EL is less, EC is more, and the triangle is pulling towards downwards, that is EC, and this is the current and this is the voltage. Current leads the voltage, the resultant voltage. We are concentrating on resultant voltage. We are not all concentrating on either only EL or IL, either only EC. We are concentrating on E is equal to IZ. This is the resultant, because resultant will pull towards downside because of the XC, capacitive reactance. So its effect is more, so it is pulling downwards. Since it is pulling downwards, here is the phi, the angle between the resultant current, only one current present, since it is a series circuit, and this is the resultant voltage. So angle is phi. This is a perfect triangle. Phi is leading, angle phi is leading. That means the current leads the voltage by an angle phi. So once again, V is equal to Vm sin omega t, and in for this I is equal to Im sin omega t plus phi, because current leads the voltage by an angle phi. We have already derived for the these two combination. We already derived the power P is equal to EI cos phi, where E and I are RMS values. When what happens if XL is equal to XC, XL is equal to XC? When XL is equal to XC, see here, there is no perfect triangle, because XL is equal to XC. If you see XL is equal to XC, the phi is equal to tan inverse XL minus XC by R. Phi is a perfect triangle, can be given. So in this formula, phi is equal to tan inverse XL or XC minus XL by R. Here when XL is equal to XC, so phi is equal to tan inverse, since XL is equal to XC, it becomes 0. So phi is equal to 0. When phi is equal to 0, so what happens? Z is equal to R, because Z is equal to square root of R square plus XL minus XC whole square. XL is equal to XC, then that term vanishes, only Z is equal to R will remain. So that means to say, when XL is equal to XC, so this will try to pull the resultant voltage upside, this will try to pull the resultant voltage downside. Since both are equal, the resultant voltage will slide over the current. That means say it is just like a pure resistive circuit, the voltage is in phase with current. That's all. So it's very important, these three combination you need to learn. Okay, thank you. And next is the power factor. So what is meant by power factor? Power factor may be defined as the cosine of the angle between the voltage and current. Power factor, if you don't know what is power factor, so you might have already came across in your labs. So power factor greater power factor, lower power factor, so everything. The power factor of the circuit is the ratio of resistance to impedance. The power factor can also be defined like this: the ratio of resistance to impedance. And power factor of circuit is also ratio of real power to the apparent power. One more derivation, so one more equation for a power factor is a ratio of real power to the apparent power, P by E into I. So maximum value of power factor is unity, and so the apparent power is a product of RMS value of current and voltage. That you already seen what is apparent power. Real power, you already seen what is my real power, volt into power factor, so that you already seen. So there is a practical importance of power factor. So the efficiency of transmission line decreases and I square R losses increases for small power factor. So I square R losses increases, efficiency decreases. So if power factor of a load is small, active power generated by generator, active power transmitted and received by consumer decreases. Is very difficult because very difficult to explain all these things, but if you know this is enough. Active power generated by generator is always generating active power, and because phi is small, that you can observe in the power triangle, phi is small, so active power generator, so it will be decreased, power transmission will be decreased. So Vi cos phi as it decreases, it will also decrease. Most of the loads used by consumers are inductive. So in industries they are all using the inductive load. So as the power factor decreased, so that would straight away affects the load. So by using static capacitors, they can improve the power factor, so in industries and all. So they can raise to